Okay, so last time we left off with we're going through this process of trying to figure out what is important in our governing equations, right? We're trying to apply our governing equations to a specific situation, which is the boundary layer. And that boundary layer has certain characteristics that might allow us to neglect certain terms in our governing equations, right? So we went through and we decided we can do this order of magnitude analysis. And by the way, I didn't write it out, but you might see it written like O of something. So we'd say O of U, partial U with respect to X or something like that. That order operator is just telling us, let's take, what is about the order of magnitude of that term. So that's how it's written out in the textbook. I think we got this far where we said, all right, we've identified the order of magnitude for all of our 1, 2, 3, 4, 5 terms here. And then the order of magnitude has to do with certain constants in the problem. So we got this far, and then what we're going to do now is let's figure out relatively how large are each of these terms, right? Relative to, say, one of the terms, how large are the other terms? So to do that, what we're going to do is divide by one of the terms, and let's divide by the one that shows up the most. So we divide through by rho u infinity squared over L, because that appears 3 times. And then we have to figure out what to do with the last 2, and this is where we left it. Okay, so let's do the last part here. Okay, so if I divide through this this 4th term here, right, divide this term by rho u infinity over L, we end up with the following. So that's mu times u infinity divided by, let's see, where are we? Yeah, what am I? So sorry, I did the wrong one already. So mu times u infinity over delta squared. And then we're dividing by rho u infinity over L. So that's then L over rho u infinity. Okay. So what do we have here? Well, let's actually multiply this by L over L. So let's make a little room here. Let's multiply this by L over L. And then this is going to give us L squared over delta squared times mu over rho u infinity times L. And then keep going with this and we get L squared over delta squared. And then what do we have? This is actually this here. Right? That's 1 over the Reynolds number. Right. So we have L squared over delta squared times 1 over our Reynolds number. All right. So actually, we're not quite sure whether that's big or small because we have something big here, L squared over delta squared, and we have 1 over Reynolds number. So a big number over another big number, right? And so how do we, what's the relationship between those two things? If we look back, actually, I don't have it on this slide, but if we look back, remember this relationship, I'll write it up in the corner here. The relationship for the boundary layer thickness, delta M. So delta M divided by X is approximately equal to 2 over the square root of Reynolds number. Okay, so we have that relationship. So if we actually use that relationship here, it turns out this becomes basically 1. Right, so this is on the order of magnitude of 1. Okay, and then the last term here, how am I going to fit this in? So let's try to squeeze this. We're going to move this a little bit. So for the last term, we'll also divide that by rho u infinity over L, and then we're left with, so this one over here is mu u infinity over L squared times L. So we take that rho u infinity squared, right? So that's our division there. If you take this one more step, that is mu over rho u infinity L, right? Well, that's just the 1 over the Reynolds number. Okay, so 1 over the Reynolds number for most situations is going to be small. So that means we went through this whole analysis and now we've decided that actually this last term here is usually pretty small compared to the rest of them. which means we can simplify our equation to get rid of that. Okay, so then doing that, our simplified equation is just rho times u du dx plus v du dy is equal to minus dp dx plus mu d squared u dy squared. Okay, so that's our simplified version of the x momentum Navier-Stokes equation for our boundary layer. Any questions on that? Pretty straightforward. The other thing to point out here is we can actually make a statement about the order of this equation, right? So if I take this entire thing, what's the order of this entire thing? The order of this entire thing is going to be as large as the largest term. So the largest term here is going to be rho u infinity squared over L. So the order of this is just rho u infinity squared over L. Okay, so we're back here. We've decided the order here is rho u infinity squared over L. So let's move on then to the y momentum. Okay, so we can go through and do the same thing. We'll do it a little more quickly for this one because you kind of know how it goes now. But we'll go through, here I've just copied the x momentum equation for reference. Okay, so the y momentum, let's see, let's take the first term here. So the first term here is going to be, this is x. So the first term here is going to be what? We have rho, we have u infinity, right? U is going to be on the order of u infinity. And then what's this dv dx, right? So v is the y component of velocity here. So that's going to be our v sub delta. That's v sub delta. And then dx in this case is going to be L. Right, that's the x length scale. Okay, second term is going to be rho v delta again. And then dv dy, that's v delta divided by, what's our y? Well, it's delta, the boundary layer thickness. So that's the order of that equation. Let's skip the dp dy for now and come back to that. So this fourth term here, d squared v dy squared, this is going to be, well, there's a mu in front, and then we have the second derivative of the y component is going to be v sub delta divided by delta squared. Okay, and then the last term here is mu in front, and then v sub delta divided by L squared. Okay, following the same kind of approach that we went through last time. So let's write this out. It ends up being rho u infinity v sub delta over L, rho u infinity squared over L times delta over L. Let's just stick with that. Sorry about that. Delta over L. I'm going to make you use your erasers today, or you can just watch me. Okay. So here we again had rho u infinity squared over L times delta over L. And here we have rho u infinity squared over L times delta over L. And then here we have rho u infinity squared over L times delta over L times 1 over Reynolds number. Okay, so that, if you kind of normalize them, that's how it ends up working out. Okay, I guess you have to take my word for it. So what we want to see here is that this term is a lot smaller than rho u infinity squared over L, right? Like delta is much smaller than L. So as we go through this and we've made these simplifications, we're seeing that the first term, the second term, the third term, all those three terms at least are smaller than the x component by delta over L, which is a significantly smaller ratio. And so actually those three end up being sort of insignificant. Right? So those end up going to close to 0 at least. If we look at the fourth term, or the fifth term here, right? this is smaller by delta over L, but it's also smaller by 1 over Reynolds number. So for sure, that's smaller. That's like even smaller than the other ones. So at least compared to the X momentum equation, all those 4 things are much, much smaller and therefore probably insignificant. Okay. That's the key takeaway here. The other part that we skipped was this thing here. So dp dy. So if we know that, okay, 1, 2, 3, 4, those 4 things are all insignificant, they're all kind of on the order of 0, then what does that say about dp dy? It also has to be on the order of 0. Right? You can't have an equation where one thing is big equal to 0. It doesn't work. So all these things sort of approximately go to 0. Right? So our conclusion here for this whole Y momentum analysis is basically that we can neglect the entire thing. Right? We can neglect the entire Y momentum part of this balance. Yeah, bottom line, we can neglect it. And actually, if you think about it, that makes sense, right? Because we have U infinity coming in the X direction, that's a significant velocity. We have V delta going in the Y direction, that's a very small velocity. So when we talk about momentum, it should work out that the Y component actually goes away.